Welcome to Challenging Climate, a podcast where we discuss the science, technology, and politics of climate change. I'm Pete Irvin, a climate scientist.
And I'm Jesse Reynolds, an environmental policy expert. Each episode, we bring on a guest with a unique perspective and deep expertise on climate change and put challenging questions to them.
In this episode, we spoke with climate scientist Patrick Brown. He is a co-director of the Climate and Energy Group at the Breakthrough Institute and adjunct lecturer in energy policy and climate at Johns Hopkins University. His work focuses on the physical and economic impact of extreme weather, which was the focus of much of our conversation.
We cover a lot of ground like we often try to do, perhaps in this episode more than others, not just extreme weather, which is the expertise with which he is most known, but also adaptation, and particularly the relationship between adaptation and economic development, the role of carefully weighing the advantages and disadvantages of, on the one hand, climate action, and on the other hand, the impacts of climate change, as well as the potential gentle tilt of some or much climate change science and science communication.
Yeah, so we cover a lot of ground, but I think there's a strong unifying strand that runs through it, which is I think Patrick is really focused on developing a grounded understanding of how the weather and its changes impact humans and what humans can do about it. And trying to be honest about it. I mean, without prompting, he did talk about the biases of the climate community writ large, scientists, communicators, and the media, and how some of these biases are generating a skewed view that is missing some of the important ways in which climate is partly beneficial or it isn't changing that much, or the improvements we've made, the development in society has made us much less vulnerable to it. So I think it's a really important episode. I think it helps give a grounded understanding of the threat of climate change, but also what we could do, how much there is for us to do to reduce those risks. So hopefully you enjoy.
And now, Patrick Brown. Patrick Brown, welcome to the Challenging Climate Podcast.
Thank you for having me.
We like to start off with getting a sense of our guest by asking them, how did you end up where you are? How did you transition from a high school kid and through university courses, I presume, and ending up at the Breakthrough Institute?
Yeah, so I guess it would start before high school. Maybe when I was 7 or 8 years old, I got just really into weather and particularly severe weather. And you actually find this a lot in the meteorological community that people tend to get into that like really young. And so I always got various weather-related things for birthday and Christmas presents, that type of thing. And I had a weather station on my roof, and I actually had a newsletter as a kid in junior high and would record forecasts on my voicemail. And so when it came to going to undergrad, I only applied to undergrad colleges that had either meteorology or atmospheric science as a major. And I ended up going to the University of Wisconsin-Madison in their atmospheric science program. After undergrad, I worked briefly as a meteorologist in the private sector, just like 6 months, but then I decided I wanted to go to grad school and I wanted to get out of the Midwest because I'm from Minnesota, so I'd only been there. And there was a interesting funded opportunity at San Jose State, a master's degree, and I wasn't sure I wanted to do a PhD yet. So I went to San Jose State in their Department of Meteorology and Climate Science, and I ended up doing some climate model evaluation. So that kind of brought me over into the climate side of things. I spent an extra year there as a lecturer teaching global warming science and solutions, was what the class was called. And that was back in 2010. So I've been basically teaching climate science for the past 12 years. After that, I went to Duke for my PhD. That was in the Department of Earth and Ocean Sciences, which is now called Earth and Climate Science. And my PhD was in unforced variability in global average temperature and kind of its relationship with the top of atmosphere energy budget. Then I kind of there was a fork in the road there where I was offered a postdoc at NASA Langley that really would have steered me down, kind of drilling down into that narrow area of what my PhD was in. And so that was kind of the career track where I would be a research scientist and kind of narrowly focused on a very specific kind of physical science question. But I decided not to go that route. I decided that I wanted to be kind of more of a generalist and more kind of interested in these bigger picture questions of human environment interaction. And so I ended up taking a postdoc with Ken Caldera in the Department of Global Ecology at Stanford. And his group is very diverse intellectually and does a lot of different things. And so there I was able to do a bunch of kind of all my papers were on different topics. But one of the things I got into was cost benefit analysis and climate economics and looking at kind of both sides of the ledger of mitigation and temperature targets. Then I worked briefly at a startup called Climate AI in the Bay Area, where we were trying to find ways to help private sector prepare for physical climate risk, which is actually more difficult than you might think. I might get into that. And then we wanted to stay in the Bay Area at that time, so I took a faculty position at San Jose State where I did my master's. And I was there for a couple of years, and then just in June moved on to being co-director of climate and energy at the Breakthrough Institute.
Bit of a philosophical question, perhaps, to launch off with, but what's the point of learning about climate science? What's the point of understanding the climate system?
That's a really good question. I mean, I always found weather and climate fascinating in its own right. So just kind of the pure science of trying to understand something better. In the current, situation with humans increasing greenhouse gas concentrations and that having implications for natural and human systems, the point, I think, more and more is to understand the impacts of increasing greenhouse gases on the climate and on people and on ecosystems. So there's different goals, right? There's applied goals, and then there's kind of knowledge just for the sake of knowledge. And you see that difference culturally at different institutions. I spent a summer at GFDL, and a lot of that research is very purely physical science based. And kind of the attitude is like, if you're studying climate change rather than climate, then you're kind of like chasing the glam. And like us serious scientists study climate. Like we study the Hadley cell. We don't study, how climate is going to change. So there's obviously different kind of subcultures. And I think, both are important, just understanding various things for the sake of understanding them, because those are the foundations of understanding how things might change and what implications, what applications those have.
I guess one thing is that there's a public understanding element. I get the sense that there's been a shift in the recent decade or so in the perception of extreme weather. It seems, or you can find media that makes it seem, that each terrible event is a clear indication that the impacts of climate change are here today and it's serious. So is extreme weather actually becoming more common, more frequent, more intense? And to what extent?
Yeah, I mean, I think the big question is to what extent? And I absolutely agree with what you just said, that when I started teaching global warming classes in 2010, I kind of felt like I really needed to convince people of, there's the common kind of saying that it's real, it's us, it's bad, and we can do something about it. And so those first two components of it's real and it's us, it kind of felt like that really needed some convincing to people. And now, like, those, I think, taken for granted, which is good because the science is extremely solid on those things. But the vast majority of the time, my kind of contemporaries who are educated people tend to be left of center. They tend to have an impression of extreme weather that's, I think, disproportionately attributes way too much of extreme weather to climate change rather than just climate. So many of these, extreme weather events like heat waves or, extreme downpours or droughts, wildfires, they absolutely can be intensified by climate change. And, in the case of heat waves, for example, it's like, I think it's fair to say that basically all heat waves are hotter than they would be otherwise. But the component that's due to climate change, I think, can really be overrated in the minds of people that are not really kind of delving into the data on these things. One kind of example of this would be when I started teaching this in 2010, we show these hockey sticks of various things. So there's a clear hockey stick, obviously, in emissions post the Industrial Revolution. And then there's obviously a clear hockey stick in concentrations of CO2 and nitrous oxide and methane. And then there's a hockey stick in global average temperature. And I remember thinking, like, in textbooks and in various presentations I haven't seen the hockey sticks in these extreme weather events or these impacts. And I thought, in my class, I'm going to go find those and show those because that's really the compelling thing. But it turns out that we don't show those because they don't really exist. Like, they're not hockey sticks. And that doesn't mean that climate change doesn't affect these things, but it means that the signal to noise ratio is relatively small, at least at 1.2 degrees Celsius warming that we've seen so far. So, we can get into the details of these, specifics, but I definitely get the impression that people that are kind of adjacent to the climate and energy space, or people that are just kind of in the energy space, do, just through the way that the media portrays it or the way that the Twitter algorithm puts things in front of you, it seems like we're in this kind of like unprecedented explosion of extreme weather that we've never seen before. And when you just look at the data, it just doesn't look like that.
Yeah, so I guess the picture is quite different depending on the impact or the weather event that you consider. We had Kerry Emanuel on a few episodes ago speaking about tropical cyclones, and that's one of the ones that obviously is much trickier to get a clear signal on because, well, there's relatively few of them, and they're also quite unique in their character, and especially in their impacts. Hurricane Katrina is not just a function of the storm, but of its specific direction and the city's location, etc. So we mentioned heat. That's one that's there's strong statistical evidence that things really are changing dramatically there. What are some of the others that it's a bit harder to get a sense of? If tropical cyclones are maybe one extreme and heat's the other, what's some things that are maybe a little surprising that are a little harder to detect?
Droughts, I would say, are one of those that are a little bit harder because you have multiple things going on. You have looking at just kind of the thermodynamic effect where a lot of the world's land surface should get essentially drier as the climate warms. And so you have this kind of background increase in aridity. And it seems like that's the main signal for droughts. But then you can have the dynamic effects potentially of, land surface atmosphere feedbacks that could kind of place certain atmospheric circulations in place for longer periods of time. And those are the things that are, very uncertain. But again, going back to the previous point, like, for example, we're in what's called a mega drought in the Southwest United States, where mega refers to the length of time, not necessarily the intensity. So it's, 20-year time period with exceptionally low soil moisture, really, because it's from the perspective of the land surface, not necessarily, just the input from rain. So it's P-E situation. But the studies that have been done on this, when you look at the, simulations of what the factual is versus what the counterfactual is, these lines basically look, they're almost on top of each other, but you can see that there's a signal from climate change because as it gets warmer in the US Southwest, that means drier. And so there's an effect from climate change. But then when this gets into the media, like the headline in the LA Times is worst drought in 1,000 years driven by climate change. And it's just kind of another thing piled on, that you get this impression that we're just in this totally, unprecedented state. But then if you look at that paper and you look at that difference between what would have happened without climate change and what did happen, it's far, far less impressive. It just gives you a very different impression than what the headline gives you. And so I would like people to be as informed as possible on these things.
So just to clarify, I mean, I think you had a comment that I thought was quite insightful on extreme heat. Well, the earliest work detecting extreme events was focused on heat waves. And there's been some events. I mean, the 2003 European heat wave is one of those ones where it's a really, really extreme event. And it's so extreme that it was near enough impossible, or so the estimates go, in a normal climate. So there's a difference between the statistical unlikelihood of an event and the actual change in the strength, the magnitude of the event. Like, can you speak to that distinction and what difference it might make to thinking about how scary these results are?
Yeah, so for the most part with heat waves, again, going back to that like dynamic and thermodynamic effects, there's tons of research trying to look for dynamic effects. And that would be a situation where you're like actually talking about the frequency of the weather patterns that produce heat waves, that changing. But that is, if that exists so far, like that is completely buried in the noise. So we don't really, that's not something that jumps out from the data. So for the most part, it's just the thermodynamic effect. It's just that you're taking the temperature distribution and you're shifting the baseline. And so the further you are out on the tail, the way that these, distributions work, kind of the more the increase you get in terms of that odds ratio. And so I do think that it's misleading to report this in terms of this odds ratio or likelihood ratio, because it gives the impression that the weather patterns that produce heat waves are increasing in likelihood, when it's really just that all heat waves are warmer. So the example that I used was the Indian heat wave, that it's two sides of the same coin. It's saying the same thing, but you can either say that the Indian heat wave from the spring of 2022 was made 30 times more likely, or it was made 1 degree Celsius hotter. And the 30 times more likely makes it, that just sounds like a much bigger number than 1C hotter. And I think, frankly, that it's sounding like a bigger number is why it gets picked up. But I think that that's kind of confusing. And it's really just that the baseline is warming. So all temperatures are hotter and heat waves are hotter as well.
And that links to, there's an idea that's been kicking around that I was definitely quite attracted to at first, but now I'm a bit more skeptical of, which is this idea of fraction of attributable risk. That, if you wanted to bring people to court for the damage done, it'll be from extreme events. And so what you can try and do is estimate, would this event have occurred and to what extent was it made more likely by climate change, and therefore the people responsible for climate change. What's your views on that concept?
Yeah, I think that fraction of attributable risk can be very problematic. So I have a submitted paper on, it's like you multiply the fraction of attributable risk times the damage that the event caused, and then you get an estimate of the fraction of the damage that was attributable to that event. And I don't think that works. And the reason why is that it basically assumes that the crossing of some threshold. So it's like an event will happen. Let's say that you have a heat wave of 38.6 degrees Celsius. And then after it happens, you define that event as crossing that threshold. And then you do this fraction of attributable risk calculation of like how much of the risk of crossing that threshold is attributable to increased greenhouse gas concentrations. And the problem with this is that it kind of imagines that if it was a little bit less hot, it would have been no event at all. So it's saying that the event, it was like absolutely critical for this event to be, considered this event. It had to cross this threshold. And if it's 1/10 of a degree less hot, then there's no event. And that's not how the damage would scale. The damage would scale with the magnitude of the event. So I think that fraction of attributable risk works for discrete things, like, if you're just going to do it on hurricanes, because hurricanes are discrete things. But it loses its meaning when it's something on a spectrum, like a heat wave or how much rain you get in a storm. And it's kind of because it was imported from epidemiology, where you do have these kind of dichotomous things, like you either have cancer or you don't have cancer. And so then you can do the fraction of attributable risk of being exposed to a chemical, the fraction of the risk of getting cancer from being exposed to that chemical. And it works because of the dichotomy, because it's either like a yes or no situation. But things like heat waves and how much rain you get are not yes or no. They're on a spectrum.
Yeah. Another key thing I think comes through in your work is that climate change and its impacts is not just about the physical change in the system, it's about the human side of the equation. And there's this pseudo equation that's in the impacts area, that risk equals hazard times exposure times vulnerability. Which has changed more? Is it the hazard that changed more, or is it the exposure and vulnerability of people in the world that's changed more over the past few decades?
Yeah, I think that is really the crux of a lot of kind of the misunderstanding with impacts and adaptation, at least historically, when you look over, the last century, that the, hazards are very impactful. So as societies, we are very sensitive to climate, and natural disasters are hugely impactful. But when you're talking about the delta, the change in the risk of impacts has been absolutely dominated by changes in vulnerability and changes in exposure over changes in the hazard. And so any type of calculation that's showing a big increase in impact risk tends to be because of increased exposure. But a lot of the actual impacts on people, we see declines over time. So we see, declines in heat deaths over time. We see declines in natural disaster, all sorts of natural disaster deaths over time. And that's because vulnerability has decreased. And the problem, what makes this whole climate change issue so thorny, is that decrease in vulnerability has been driven by our kind of fossil fueled development. So we have, all of this infrastructure and high energy lifestyles and ability to make dikes and dams and ability to have insulated buildings and to heat them and cool them. All of that historically has been made possible by fossil fuels. And so historically, fossil fuels have protected us from climate much more than they've harmed us from climate. And that's what makes this difficult. That's what makes kind of the cost-benefit analysis equation relevant here, of how much are you willing to sacrifice energy-wise and development-wise to help people become ostensibly more resilient to climate. But you can very much get that wrong, where you can be too worried about, decreasing emissions, and so then decreasing the hazard, where you're going to sacrifice the decrease in vulnerability.
And a decrease in vulnerability is one of the primary goals of what's often called climate adaptation. And so I want to dive a little bit into an essay that you co-authored with your colleagues Ted Nordhaus and Vijaya Ramachandran in Foreign Policy, called The Obvious Climate Strategy Nobody Will Talk About. Wonderful title. And sometimes one can see adaptation as the neglected step cousin, if you will, in climate policy debates, with so much attention going to emissions reduction. But you write in this essay, quote, "The basic formula for adapting to climate change is the same as the formula that has allowed the world to radically reduce the human costs of climate-related disasters over the last century: more wealth, infrastructure, and technology." And basically what you're describing is economic development. So what's the useful way to think about the relationship between adaptation and development? Is adaptation a subset of development? Is it an overlapping circle? Is there a causal relationship between the two?
Yeah, I think in the climate discourse, there's really too much emphasis on adaptation itself. Because adaptation makes it seem like the only motivation to become resilient to nature and to climate and to natural disasters is because the climate is changing. So we need to adapt to the changing climate. But really, it's just the baseline climate itself. You don't need a changing climate to increase resilience. And the differences are just totally stark across the world today. That if you look at deaths from natural disasters, it's 95% of deaths from natural disasters are in developing countries, and there's other studies that look at that it's like 15 times more likely for a given disaster, 15 times more likely to have a death in one of these vulnerable low-income countries. And so it's not so much adaptation as it's just, we hear a lot about climate emergency, and that's really focused again on the hazard. But I think the real, climate emergency is that vulnerability piece, where you have, a billion people or close to a billion people. Luckily, this number is going down, but close to a billion people still without any access to electricity, and 3 billion people in, what's considered energy poverty, very, very low energy lifestyles, because they're in poverty. And you look at, just pictures of these cities. I show a picture of basically a slum in India versus Singapore. It's just so clear, like, which society is going to be more resilient to a downpour of 10 inches or to a heat wave. And so I guess the point here is just that we want to facilitate economic development and the infrastructure that comes from that, and the energy, it's, high energy, much higher consumption lifestyles that we take for granted in the modern world. We want to facilitate that if we are centering human well-being, and particularly, material well-being, in an effort to increase resilience to climate. And then that naturally also makes us more resilient to climate change. So then you have that adaptation. But again, I don't really think it's we're anticipating change and adapting as much as it's just kind of this natural background. Economic development makes us more resilient to all things. And of course, then, many other aspects of life increase as well.
That raises a thorny question. If one is interested in improving human well-being, particularly those who are toward the bottom end of the scale of human well-being, in the context of acknowledged anthropogenic climate change? What position should you take on fossil fuel use? I mean, because, phasing out fossil fuels is the mantra of the contemporary climate movement, but should it be, particularly when you look at a developing country?
Yeah, I mean, the problem with CO2 is that it accumulates in the atmosphere and the sinks are very, very, very slow. And so it absolutely is the case that we need to get emissions to zero in order to stabilize temperature, right? Not bring it down to where it was previously. And even once you do that, you've probably committed large portions of our ice sheets to melting. So you're going to have sea level rise for hundreds of years. And so getting that right, where you are trading off against potentially inhibiting development and keeping people more vulnerable to climate change currently, kind of for trading off future well-being. That is the situation that we're in, and it's very thorny, and I don't have an answer to that, and I don't know what the right answer is. But I do think that we should acknowledge that that's the situation that we're in, and that it's not some situation where kind of what I hear is, so, we've had this like 97% consensus number, which applies again to those first 2 points of it's real and it's us. But I think the climate kind of activist movement has successfully but erroneously applied that to these temperature targets or these goals that, quote unquote, the science says that we have to remain below 1.5 degrees Celsius of warming. But the science cannot say that, because that involves all of ethics and morality and philosophy and trading off well-being of different entities and looking over time and discounting the future and all of these different things. And so I just think that we should be honest about that and not pretend like the science could tell us exactly the speed at which an energy transition needs to occur in order to optimize, whatever.
So, on the topic of temperature targets and optimization, we do hear a lot about the 1.5 goal in particular. That's the more ambitious goal of the Paris Agreement, the lower goal in the sense that lower is what you want. You want less warming, so that's more ambition. And the higher goal being 2 degrees warming. Yet some climate economists who operate integrated assessment models have said that a higher amount of warming might actually turn out to be economically optimal. I've heard various numbers. We're going to draw a bit from a paper that you wrote in PLOS 1 from earlier this year that we'll link to from our website on the approximate calculations of the net economic impact of global warming mitigation targets. Why are there such wide ranges in what warming goals should be? Why can some people point and say the science says 1.5 is a critical threshold, and others say maybe 3 is not so bad?
Well, I think different people have different moral goals. So if you are extremely worried about warm water corals, then, it is absolutely the case that breaching 1.5 is extremely, extremely dangerous. If you are trying to optimize for, in this model, the DICE model, that optimizes global utility integrated over time with a discount function. And so historically, that has always been above 2 degrees Celsius as what the optimum level of warming would be if you're trying to optimize for human utility. And those are extremely, extremely uncertain things, right? You just think about projecting society into the future and how many variables could possibly change and what GDP even really is and how to convert that into human well-being. There's just a million different questions that come up. So naturally, that's going to be extremely uncertain. But yeah, I think that is the true situation that we're in. And it's not so easy as just, net zero by 2050 is what the science says. And those actually do get called science-based targets. And the science-based target wording there refers to the science is about how quickly you have to reduce emissions in order to stay below those temperatures. But it's not referring to that this is some threshold that cannot be crossed or that economic activity couldn't be optimized if it was above that threshold.
Is some of the difference among warming targets that are espoused not just differences in values, but differences in methodology? Is there in some quarters of the climate change community a neglect of the costs of climate action?
Yeah, I think that just kind of taking a step back and looking at the literature and looking at the energy and climate research communities in general, so much of it is basically goal oriented around trying to find impacts and basically publishing on those and downplaying costs of reducing emissions. So kind of cheerleading for renewable energy. And that comes out of just natural kind of social dynamics of kind of everyone wants to be on the right side of history and have research that's contributing to pushing society in the right direction. But then it's very difficult to take the literature at face value when you know how many more people are oriented in that direction, where it's overemphasize the benefits of reducing emissions and de-emphasize the costs of that. And so, I wish, for example, the IPCC, I think a more useful organization rather than the Intergovernmental Panel on Climate Change, which is focused on a negative side effect of a particular energy system. It could be the Intergovernmental Panel on Costs and Benefits of All Energy Systems. And so that would be a more holistic entity that could potentially tell you what the optimum energy mix over the next century. I mean, this is a very difficult question to answer, but at least like that would be oriented towards answering that question rather than oriented from the outset towards moving away from fossil fuels, which is kind of what the whole organization is oriented towards.
And in addition to the possible neglect of costs for whatever reason and differing values, there's the question of how to value the future. I'm going to have to be a little bit nerdy here, which may enthrall some of our listeners and may deter others. And economists call this the discount rate. How much do we discount the future? Everybody discounts the future. If you had the choice between receiving a cash prize today or next year, most people would choose the cash prize today. And they'd probably even choose a smaller cash prize today than a slightly bigger one in a year. And it's not irrational because there's other things you can be doing with your money, like investment. And it's not irrational because the future's uncertain. But I've seen wildly divergent climate policies ultimately hinge upon the discount rate that is largely assumed. And this is tricky because it's an intergenerational discount rate, which raises moral questions because you're making decisions that impact future generations that might not be born yet and certainly don't have a voice in current conversation. So it's not my cash prize. It's my prize versus the potential larger prize of my great-grandchildren, if you will. How can policymakers navigate this treacherous path between the good arguments for a low discount rate and a high discount rate, particularly in the intergenerational context? I think within when a given person, there's enough human behavioral studies to have a sense of what people do and how people act. But we can't do that in the intergenerational context. What to do?
I mean, the short answer is I don't know. Yeah, the discount rate is the knob that you can turn in those models that is the least constrained by data. It's a kind of a philosophical thing. And it's very impactful on the number that you get. In the DICE model that I used, it's interesting because the lower the discount rate, so the less you discount the future, the more stringent you want to mitigate climate change, because you just have like generations kind of infinitely into the future being damaged by climate change. But you do notice that there's kind of this assumption built into that future generations can't adapt to climate change. So it's the way that the damage function works in the DICE model. Once you're away from pre-industrial climate, you're taking a GDP hit every single year, no matter what. So then the more you incorporate well-being into the future, the more that you want to make sure that those people aren't taking that GDP hit every single year. And that doesn't, strike me as correct. Like it seems like when you look, across space today, that we span like 20 degrees Celsius temperatures, and you look at how the impacts from climate change, like heat deaths, have decreased over time. The idea that if it warms 2 degrees Celsius, that all future generations are continuously damaged every single year because of that doesn't really make sense. And so that all is intertwined with this discount rate and thinking about the deep future. And yeah, I mean, that's just an assessment of how thorny the issue is. There's not an answer that I know of that's satisfactory.
You shared a draft of a report of a sort of a literature review about heat deaths or temperature-related deaths. I think kind of brings this home a little bit. And it has some interesting statistics. I'll just mention this one that sort of caught my eye. There's roughly 5 million excess deaths per year associated with temperatures being too extreme, but only 10% of that is due to high extreme temperatures. So yeah, can you give us a little more on this, on temperatures and mortality, and how that's changed and how difficult it is to make projections of that into the future?
Yeah, so I wrote this literature review on the research that's been done on temperature-related mortality, so being away from the optimal temperature. And yeah, some interesting things come out of that. One is what you just mentioned, that cold deaths are about 10 times more common than heat deaths. And by the way, this is all statistical relationships. So these deaths are usually cardiovascular or respiratory deaths, but you can see it in the statistics that when there's a deviation in temperature, you get like an increase in death rates. But these are all statistical associations and it doesn't go on your death certificate that you died of cold. So, that's one thing. And that tells us something about the filter by which we're receiving research information, because that's kind of, really interesting and relevant to the conversations we're having about climate change, but it's not something that's well known, right? And so because cold deaths are more common than heat deaths, that doesn't necessarily mean that as it gets warmer, you would have a decrease in deaths. And actually, because of the shape of these functions, it's much steeper on the warm side. And so warming, there's some reason to believe that as it warms, you would increase heat deaths more than you would decrease cold deaths, even while cold deaths remain higher than heat deaths, but you would get a net increase in deaths. But actually, the research that's been most detailed on this has not shown that, and has shown, since we've had really good data since 2000, that warming by itself has saved more lives than it's taken. And so, again, that's something that basically doesn't penetrate into the media because it's a data point that's not convenient for this broader narrative. And that's, I think, a problem in our community, is that there's all these selection effects going on where, you have selection effects of people that go into climate research, that these are the people that tend to be most concerned about climate change. And so naturally, they're going to be oriented towards asking questions, research questions, where the answer has something to do with, like a large impact from climate change. And then we have the situation where you can change the question a bunch of different times as a researcher. Like you look for something, you don't find it. You look for something else, you don't find it. You look for something else, you don't find it. Eventually you find some impact. And then you write a paper on that. And then there's constraints from peer review, but you have infinite time to submit your paper a million different times, right? So you can argue with reviewers, or you can go to a new journal, and you have thousands of people doing this where their mental faculties are oriented in a way to try to find and emphasize negative impacts from climate change. And so what results from that process is something that I don't think is actually representative of what would be the case if you just kind of took like a top-down approach and said, let's look at, these are like the 5 candidates of biggest impacts from climate change. And ahead of time, we're going to say like, these are the ways to measure those. And then let's just do that. Let's just like look at, what are the trends in these various things. You get a very different impression than what you get from this bottom-up approach, where everyone's kind of looking for a particular answer. And what ends up making it penetrating into the media will be the only things that do get, that answer. And, I experienced this, of course, throughout my whole career. Like the first project I was put on as a PhD student was kind of the previous PhD student and my PI had shown that under climate change in the summer, the Azores high gets more intense by some measure. So this is the high pressure system in the Atlantic. And my job was basically to connect that to hurricane tracks. And it's not like explicitly spelled out to me or whatever, but it's just obvious that what we want to find is that this thing steers more hurricanes into the United States. Like that's going to be best for everyone's career. That's going to get the highest profile paper. And so that's just kind of what's going on everywhere in both the physical science side of things and the impact side of things. So I sliced and diced the data a million different ways. And there's so many researcher degrees of freedom. There's so many, oh, let's do an EOF on the tracks, or let's do some clustering analysis on the tracks. And you're looking for a particular answer because you want this cohesive paper, this nice story. I ended up abandoning it because I couldn't find it. But then that's the file drawer effect, right? There's no paper that comes out and there's no headline that says climate change doesn't impact storm tracks. That doesn't get to the surface. So going back to the heat and cold mortality, you just have these selection effects that don't allow these results to get to the forefront. And some other, interesting aspects of that literature review are that heat deaths by themselves, so if you isolate for heat deaths, they've declined almost everywhere that they've looked. And so again, that's that vulnerability totally predominating over the increase in the hazard. So the decrease in vulnerability from economic development and air conditioning dominating over the increase in temperature. And again, this is something that I think the IPCC, the impacts and adaptation chapter, or the whole working group 2 report, that should be like a whole chapter, is like, why have heat deaths declined despite warming? Because we need to understand this as best as we can so that we can facilitate the best adaptation to temperature change in the future. But instead of that, the whole report is kind of oriented around we can't adapt. And so it's like making this case of, adaptation doesn't really work. And so then working group 3 shows us how to reduce the hazard by reducing emissions. And so I think there's some real, neglect there of obvious solutions that would really help people.
Just want to pick up something briefly on you're mentioning these, I guess, the biases, the ways in which the climate community, and I guess I think an important player are sort of the nature and science editors who sort of shape what is a big career-making paper, how they shape and how it's distorting in a way and gathering certain strands of the climate story together and excluding others. One interesting sort of note here I've spotted working on solar geoengineering is that the unappreciated benefits of climate change reappear in the solar geoengineering literature as the terrible side effects of solar geoengineering. There was one paper recently that showed, there'd be a massive increase in malaria deaths in the developing world under geoengineering because climate change causes such enormous impacts on the ecosystems that it basically pushes the malaria out of the tropics. And so by reversing that benefit of climate change, you have a risk of solar geoengineering. Small side thing, but they're coming back, I think. I think those benefits. So speaking of these biases, I think I grew up, or sort of I entered the climate community, I think I'm probably about the same time as you. 2009, I started my PhD. And I think at that time, we were at the tail end, or perhaps even at the peak of the climate denial, its impact on the discourse and how it was, I think the world was just beginning to reckon with the fact that they'd being misled on the reality of the changing climate. And I think that scarred our community and shaped perceptions of people. And I wonder if what we're seeing now is the pendulum has yet to swing back. We've got a new climate communication problem, which is a growing sense of doom that's developing in many young people, quite understandably, because, people don't experience, all weather extremes. We experience some from time to time, but what we perceive as the impacts of climate change are shown to us by the media. And there's all these filtering effects that you've been talking about. So seems to be many people that have got this perception that we're really, really on the edge of collapse or we're doomed on our current trajectory. What are some practical things that the climate community should be doing to try and make sure they communicate that climate change is serious, but it isn't life or death for the planet? It's not the end of the world. How do we go about that?
Yeah, that's a tough question for me because I resist the idea that we have this kind of meta responsibility to push society in one direction or another, that we have this kind of ends justifies the means type of thing with, climate communication. Like, I think the role of a scientist is really to be more narrow in terms of reporting facts, and that it's an easy thing to call things facts, and it actually kind of breaks down when you try to interrogate what exactly a fact is. But to be just honest with what the impacts are that we're seeing, and to not do this, well, if I say this, it might undermine the larger case, and the public can't handle the truth. Like, we're going to have to kind of massage this so that they get the right message, they get the right impression. And I don't want to be thinking that other experts are doing that in other fields. I want to know from epidemiologists what the risk of death is from COVID or something. I don't want them to exaggerate it because they think that I can't handle, probabilities or whatever. Like that is the reason that we give science such a privileged position in our society in the first place, is that we think that scientists are giving us kind of just the facts, and that it's up to politicians and it's up to the public to take those facts in and to make informed decisions. And you can't have it where, every single group, the climate scientists say that climate is the most important thing, and these other scientists think their thing is the most important thing. Like, then everything breaks down, and it's the same thing as having no information at all. So I'm I'm avoiding the question, but I don't like the idea of my job as a scientist is to communicate like the right message and get that through. I think my job is to report what we're seeing, and then it's up to people to kind of take in that information. And sometimes you have, 6 data points in one direction and 4 in another, and they have to weigh that and figure out what the best option is going forward.
So to wrap this up, we ask our guests in this context of what is often a daunting task in front of humanity, what gives you optimism about the future, and specifically, but not necessarily only, regarding climate change?
What gives me optimism is all of the success that we've seen historically. So people are under the impression that everything's, going to hell, and we're seeing all this unprecedented extreme weather that is causing all of this damage that's never been seen before. But if you look historically, we have these dramatic decreases in poverty, dramatic decreases in hunger, increases in the standard of living, increases in literacy, increases in lifespan, decreases in infant mortality, kind of all of the measures of human well-being, increases in people living in democracies. All of these things are going in the right direction. And a lot of that historically has been facilitated by fossil fuels. So we have this problem where we need to transition away from fossil fuels in order to stabilize temperature. Or we at least need to capture carbon. We need some situation where we're not continuing to put carbon into the atmosphere. But the successes historically make me optimistic, that we can do this. I think, 1.5 and 2 degrees are basically off the table. Like we see that at these COPs that, we're on COP 27. And if it was easy to transition away from fossil fuels, we would have done it a long time ago. It's hard, but we are pushing in the right direction. In major industrialized economies in the United States and Europe, emissions have peaked and they're coming down. A lot of that is from switching from coal to natural gas. And there's also kind of a decrease in energy used per person, which is interesting. But, solar and wind are becoming much cheaper and much more realistic to power an electric grid with, and electric vehicles themselves are maturing and becoming cheaper. So, we can see the energy transition on the horizon, but I don't think it's going to happen nearly fast enough to meet these rather arbitrary temperature targets. But I think the best bet is that the rest of the century, we continue to see a lot of these positive trends in human well-being, and we gradually shift away from fossil fuels. Not net zero by 2050, but maybe net zero by 2100.
Our guest this episode of Challenging Climate has been Patrick Brown of the Breakthrough Institute. Patrick, thank you for joining us.
Thanks a lot for having me.
Well, thanks for listening. Please rate or review us on Apple Podcasts and elsewhere, and consider supporting us on Patreon. That's patreon.com/challengingclimate.